So Calvin, you said the question that came up for you the most from the unit test was, how do you know if a bond is forming or if a bond is breaking? I want to go through an example that I gave on that worksheet from last week. How many of you guys were able to go through that worksheet and complete the rest of the arrow pushing on your own? Good. Did anybody take advantage of the video that I posted? Great. This problem gave us two arrows. There was one arrow that started from the negative charge and went to the carbon that is double bonded to O. Another arrow that starts at the double bond between C and O and moves up to the oxygen. If a bond is breaking, then your arrow starts at that bond. The arrow says, pay attention to these two electrons that make up this bond. These two electrons are going to leave the bonding region. And they're only allowed to go to the oxygen or to the carbon or to another bond with the oxygen. Because oxygen owns those electrons, it can control what they do. They'll really never come down to the carbon. So here, we're saying that the electrons will go to oxygen. That's a CO double bond breaking. A bond forming will start from an unshared pair of electrons. So for instance, the lone pair on the carbon and cyanide. And it will go to a nucleus in order to form a bond from that unshared pair to a new atom that it can share with. Or it will go into a bonding region where there already is a bond, and it will create an additional bond, a double bond or a triple bond. Bond forming to carbon, bond breaking to oxygen. We can look at a few more examples. We had another compound on this worksheet last week where we saw water deprotonating a hydrogen from a carbon. Here we've got our Bronsted-Lowry acid, and here's our Bronsted-Lowry base. Oxygen will form a bond with hydrogen. So again, a pair of electrons not in a bond going to a nucleus that will form a bond. And then we have a CH bond breaking. The electron arrow will start at that electron pair, show that the bond breaks, and then the electrons will end at another bond. If there's already one bond there, and I'm indicating that two more electrons are going there, now I'll have two bonds in that region. I already have two electrons, I'm adding another two, it's a double bonded region. So this arrow actually indicates all at once bond breaking and bond forming. So there's not necessarily one clean-cut way that bonds break and bonds form. But if you have an arrow starting at a bond, you know that bond is breaking. And if you have an arrow pointing to a new atom, then you know that bond is forming. Do you think that helps wrap it up? Okay. Anything else you guys want to talk about from Unit 1 before we dive headfirst into Unit 2? Did Unit 1 feel like general chemistry? Some nodding, some shaking. I tried to design Unit 1 to feel like the bridge between general chemistry and organic chemistry. We talk about a lot of the concepts that we introduced in Gen Chem, but we spend a lot of time looking at organic molecules because we have to get familiar with them fast, because they're going to be the only thing we look at all semester long. And I think in a lot of ways, it doesn't really feel like general chemistry, because in Gen Chem, you go over so much content that you never spend time thinking about and talking about formal charge. Maybe when we discussed acids and bases, that felt more like Gen Chem. But it's a whole different language. It's a whole different side to chemistry. Today's lecture is going to introduce us to two of the most important concepts in organic chemistry. One of them is stereochemistry, and the other is regiochemistry. I'd like you guys to talk with each other real quick. And I know you've been building relationships with the people that sit near you, so soak that in while you still have it. Chat with the people around you about what you think these two prefixes are trying to tell us.
People been dropping?
No.
Are you gonna mix this up?
Yeah. Well, we'll see if your friendships make the cut today. Talk for about a minute about what you think these two things are telling you about the chemistry that we'll explore. What is coming across? About your test.
Yeah.
Yes.
So I started and I left it. I'm gonna start tomorrow. And then
I meant to message you back and say that I will still accept it. I looked at the timing and the questions that you put in. Yeah.
So do we have to finish it as soon as we started? Like we can't.
It's a timed exam. Yeah.
Because I know, like, I thought in previous classes I had,
Mm-hmm.
there was a timer, but then when I left and to do it like the next day, it was okay. I was like, so
I don't know. I guess I don't know how that would work. My understanding with Canvas is when you press begin, it will start that timer, and regardless of what you do. I've had students whose like computers die or their internet cuts out and the timer just keeps going and they can't even get back to it. The idea is once you see the questions, I want to see you answer them in real time. I don't want someone to be able to look at the questions, ponder them, sleep on it, come back the next day and do it.
yeah, because like I finished the first part and then I opened the second one. I was like, my brain's not ready to do it.
Yeah.
Going back.
So you still had access to it.
Well,
When you came back,
when I came back, it said
closed,
closed.
but you're able to see the response.
Basically, yeah.
And then did you just set a timer?
I mean, I did it again.
Yeah. Did it take you 60 minutes?
No.
Yeah, I didn't expect it to. So that's another reason why I wasn't too concerned about it. But I appreciated you reaching out.
Yeah. I was like, oh no.
I appreciate you taking the initiative to just do it, because I've had students that run into issues and then they're like, can I do it? Yeah, you have the questions. You can still access them. Just do it. So that was easier for me. All right, what do you think? Did you, have you heard these terms before? Layla, you have? Which one, both? Wedge and dash. And where did you hear these before? Yeah? Stereochemistry. When you're learning about molecular shapes, electron domains, molecular geometry. Regiochemistry? No, probably not. So maybe from your reading, or you just kind of made sense of it. Regio, region, tells you what's bonded to what. Was that it? Perfect. Did I miss anybody? Good. Anybody else have anything to add to those terms? Regiochemistry, stereochemistry. Anything that it kind of provokes in your mind when you hear those prefixes? Does stereo make you think of something? Turn up the stereo. What is that supposed to get at? When we refer to a radio as stereo, do you know what we're implying?
Like AM, FM, or something else?
Not AM, FM, which I think comes down to the way that you measure the frequency. Left and right on the speakers, yeah. My dad, when I was in middle school, installed stereo surround sound in our living room. He had these wires that went from the TV into the ceiling and then had these speakers in the corner of the room. Stereo surround sound was the biggest thing. So this is meant to tell us about spatial chemistry. Spatial implications. We can talk about molecular geometry as stereochemistry. For instance, if I were to draw a trigonal planar carbon with a cation, we call it a carbocation. We know that this is trigonal planar because there are only 3 electron regions. They repel each other as much as possible. But it looks just like a flat drawing. I can turn this onto its side and represent its stereochemistry with these wedges and dashes. And now I can actually better see that it is a flat species. I can see that there's a plane coming out towards me and away from me when it's on its side. I can see that there is an empty p orbital that sits on this carbon, and that p orbital is perpendicular to the plane of the groups. We can do something similar with linear geometries, but it looks really goofy to have something that is a line and then to have something that is a line coming towards you and away from you. Just kind of looks silly. But this is also what we do with tetrahedral groups. When I've got an sp3 hybridized atom, it doesn't make sense to leave everything in plane. Instead, we represent the 3-dimensional orientation, the stereochemistry, with things, one bond coming towards us, one bond going away from us. There is one thing that I want to hit on, especially with the tetrahedral carbon. And to do that, I'm going to show you guys a resource that you have access to. If you take this external resources link on our homepage, you could do this on ChemTube 3D, but the website that I think is a little bit better for this is Visualizing Molecules with SimOtter. This will allow you to do a lot of different compounds, a lot of different things to explore here. I just want to take a simple sp3 hybridized atom, and I want to try and illustrate this stereochemistry of the tetrahedral carbon with it. Here, I have a bond in plane going up and a bond in plane going to the left, just like I've drawn it here. And then I have a group coming towards me and a group going away from me. Sorry, my little camera's in there. What a lot of students will instinctively do throughout the semester, they'll take this beginning structure and they'll just kind of randomly assign a wedge and a dash to it. So you'll see how I kept the left and the right bonds in plane, and then I just made one group go up and one group go down. Draw this if you want to draw an X over it. Otherwise, don't draw it. This doesn't exist. It can't exist. It's a misinterpretation of the stereochemistry. We can use this model on SimOtter to try and prove that. If I try to get one line in plane going left and right, then I'll try to look for a group coming towards me and a group going away from me. Okay, I'm going to use the green line to go in plane, and I'm going to have this other line going to the left also in plane. Okay, I have a group coming towards me and a group going away from me, but you'll actually notice that they're both going up. There's this vertex of the two bonds that are in plane. They create this vertex, and out of that vertex, I have a group coming towards me and a group going away from me. I do not have a group coming towards me above that vertex and a group going away from me below that vertex. Do you agree that this does not look like this? If I twist it this way, such that I have something above and below that vertex, well, actually now they're both pointing towards me. They're both wedged. And these other two bonds that I had used to be in plane, just lines, they're actually both dashes. They're both going away from me. All right, let's just try finagling it a little bit more. I'll twist it down to the bottom, but we see the same thing. Whenever you have a wedge and a dash, they will always come out of this vertex from the two lines that are in plane. This is the appropriate way to represent the tetrahedral stereochemistry. And I hark on this because next week we're going to be doing analysis of molecules using this information, using the wedged and dashed groups coming out of an sp3 hybridized carbon. And if you don't draw those groups appropriately, you cannot appropriately analyze the compound. You will misinform yourself about important characteristics of these carbons if they're drawn inappropriately. Stereochemistry. Another application of stereochemistry, we'll get into this more next week, but these are stereoisomers. You know what isomers are? Isomer is composed of two parts. Iso, meaning the same, identical, and mer, meaning like mermaids. No, meaning units. Identical units. Stereoisomers have identical units that differ by their arrangement in space. A quick example of this, small molecule. It's a four-membered carbon ring. We call it cyclobutane. If one of the carbons has a bromine bonded to it, and that bromine has a stereochemistry wedged towards you, and another carbon has a bromine that has stereochemistry dashed going away from you, we can refer to these two groups as having the bromines on opposite faces of the ring. One up, one down, one wedged, one dashed. And we call this a trans configuration of those two groups. That is a different molecule than when both bonds are wedged or both bonds are dashed. Their stereoisomerism is cis-trans. This is how we refer to it. There is a whole other class of stereoisomers that we're going to get to next week. This is just our introduction for today. Questions on stereochemistry? chemistry, stereoisomers, the way things take up space. Okay, regiochemistry. What does this provoke in your mind? The region. Do you know what I think a lot of students struggle with in Gen Chem 1? Is learning about molecular geometry and not realizing that it does not describe the entire molecule. When we look at a specific carbon and we say that atom has a molecular geometry, trigonal planar, what we're saying is relative to that carbon, the rest of the molecule is oriented trigonal planar. So its molecular geometry is trigonal planar. But the molecule as a whole may have many molecular geometries. It comes off as a bit of an oxymoron to Gen Chem 1 students, understandably. Regiochemistry may feel similar. This has everything to do with bonding regions. Regional implications. The first one that I want to talk about, because functional groups was a great answer for that, Layla. But the first one that I want to talk about in regiochemistry is a little bit simpler, and it comes down to degrees of substitution. This is how we refer to it, but strictly speaking, we are talking explicitly about carbons. And this will describe how many other carbons a carbon is bonded to. So much like we can look at a carbon and describe its molecular geometry, we can look at a carbon and describe its degree of substitution. The first degree of substitution really is non-substituted. We call these methyl carbons. That's a carbon that is bonded to 0 other carbons. You've heard of methane. You've heard of methanol. There are many, many more. These carbons are bonded to other things, but they are not bonded to other carbons. Then we have primary carbons, which will represent as this 1 degree, but we'll say as primary. These will have 1 bond to another carbon. A lot of times, when we look at CH3 groups on the end of a molecule, these are all primary carbons. I think I'm going to have to make more space. So you guys are good on the stereochemistry if I erase it. So let's draw a small molecule. And we'll use bond line structure. Boy, it's real small. There's only 2 carbons in it. And both of these carbons are primary. They're both bonded to 1 other carbon. If we try to go for a bit of a bigger structure, a CH3 a COOCH3. This structure has 2 primary carbons. You can actually see that this carbon-carbon chain is very similar to our first carbon-carbon chain. Those carbons are only bonded to one other carbon despite the fact that the rest of their bonding environment is very different. And how would we label the substitution of this? Non-substituted. This is a methyl carbon. Okay, our next is secondary, represented as 2 degrees. This has 2 carbon-carbon bonds. I'm going to represent that as a central carbon that has 2 other bonds to carbons. Couple of compounds for us to consider here. Rubbing alcohol, isopropyl alcohol, has a secondary carbon right in the middle and 2 primary carbons on the outsides. Are we jumping too fast? Does it make sense why we can look at every carbon and assign it its own degree of substitution? Acetone, nail polish remover, also the magic eraser in the organic chemistry lab. This is an oxidized version of isopropyl alcohol. It has the exact same regiochemistry for its carbons. It has a secondary central carbon, primary exterior carbons. When we move to 3 bonds, we call it tertiary. Here, our central carbon is bonded to 3 other carbons. We'll be using this molecule a lot. We call it tert butoxide. And that tert at the beginning, tert butoxide, is actually referring to the fact that the central carbon is tertiary substituted. This carbon in the middle is tertiary. All other carbons in the structure are just primary. Let's start getting some cyclic structures in here as well. Here I have a 6-membered ring. One of the carbons in that ring is bonded to a chlorine. One of those carbons in the ring is bonded to a CH3. How many carbons in the ring are tertiary substituted? Two? 1? We're torn. Annie, do you want to try and give your reasoning?
Well, the other one's chloride, so I'm trying to debate, like, I feel like if the other one was just carbon, that would be fine.
So this one here is tertiary, for sure. That central carbon has the carbon bonded to chlorine, a CH2 and a CH3, 3 carbons. And this carbon up here, it has a CH2 on one side and the tertiary carbon. But the chlorine does not count as a bond to carbon. So when describing its regiochemistry as substituted, this is still a secondary substituted carbon. As are all of the other carbons in the ring, except for the methyl group, the CH3. The CH3 is considered primary. And that's it. That's the highest it can go, yeah? You can't substitute a carbon anymore. Why not make all 4 bonds to that carbon carbons? This we give the term quaternary. And don't worry, I won't ever quiz you on how to spell it. But this is describing that carbon that is bonded only to other carbons. This doesn't happen a lot, but it does come up. And there's a lot of different ways that it can come up. Quaternary carbon in the middle of this compound called neopentane, and a quaternary carbon at the carbon in the ring with two CH3s coming off. Do you feel confident you could label the substitution of all of the other carbons? Great. Dipping our toes into the world of regiochemistry. That's all we're doing here. Okay, the second, probably the more influential type of regiochemistry, functional groups. You know what? I did want to mention, I avoid giving terms like primary, secondary, tertiary, and quaternary to carbons that are in carbon-carbon bonds. Why? One, there's no good consensus on it, so not everybody would agree with using the same label. There's no standard for it. Two, it is a bit tricky. There is no good reason to lean one way or the other. Remember, we said it's based on the number of carbons that a carbon is bonded to. Well, this carbon at the top is bonded to one other carbon. So that makes it seem like it's a primary carbon, but it has two bonds to carbon. So that makes it seem like it's a secondary carbon. So the distinction between is this primary or is it secondary is not well answered. So I will typically avoid assigning substitutions to things like that. What we can say is less substituted and more substituted. We can definitely say that. The carbon on top is the carbon on top is less substituted. It is bonded to less carbons and has less bonds to carbon. Whether we agree on primary or secondary doesn't quite matter, as long as we can say it's more substituted and less substituted. Okay. How many of you have heard of functional groups before you come into this class? Yes? In what context have you heard of it before?
I did take bioorganic chemistry.
1120?
It was at BYU, so I don't know, but it's probably, yes, the same.
What other contexts?
Biology.
In biology. Okay. So you guys have a little bit of a grasp on this. For those that maybe have not heard this before, what would you call a functional group? How would you define it? Is it tough, or you just don't want to?
Something that gives its characteristics.
Gives characteristics. Good. Involves specific atoms when those atoms give certain characteristics. Involves certain atoms in certain bonding patterns, because the same atoms can be bonded in different ways and give very different characteristics. So functional groups are sets of atoms in specific bonding patterns with unique characteristics. So you all have this sheet in front of you. I made this a few years ago. I know that yours is black and white, so it might not show up well, but this is available on our homepage, or sorry, on our class resources from the homepage. And when you look at it on our homepage, it will actually have certain atoms in specific bonding patterns that are highlighted in red to showcase the specific functional group within that molecule that's being highlighted in that example. True or false, any given molecule has only one functional group. Definitely false. Which is why in biology we refer to things like amino acids, which have at least an amine group and a carboxylic acid. Always those two, and oftentimes many other functional groups. This is not an exhaustive list of functional groups. This is a lot, but it's not all of them. It's the ones that we will see this semester and next semester in OChem 2, and it's the ones that I want you to be the most familiar with. When people say organic chemistry is a memorization game, this is really the only thing that you can memorize, and memorizing it is a challenge because you need to be able to apply it to specific molecules. You need to be able to recognize those bonding patterns when they're not explicitly highlighted, when they are cluttered by a lot of other functional groups. That's why your next assignment for analyzing your organic compound is to identify all of the functional groups in your compounds. So use this as a tool. Lean into this. My recommendation, every time you see an organic molecule, and you'll see a lot, go back to the ones you've already seen, identify those functional groups that are in it. Do this as often as you can to start getting more and more familiar with these functional groups. There are a few things that I want to point out about functional groups. Sometimes you have these repeat sets of atoms that are now in distinct bonding patterns, which separate them from other functional groups. If you'll look on the top left, we say that an alkene is characterized by a carbon-carbon bond, a carbon-carbon double bond. And yet, we describe an aromatic ring as a cyclic, six-membered carbon ring with 3 carbon-carbon double bonds. There is no alkene inside the aromatic ring. Despite the fact that our definition of alkene can be applied within the aromatic ring takes a bigger context. And so alkenes are not present in aromatic rings. We don't say that there is an aromatic ring plus an alkene. We're not doubling up. A few other instances where we don't double up. Alcohols are represented as ROH. R here generally represents carbon. We'll use it to represent the rest of the molecule. A carboxylic acid also has an OH group, but that OH is bonded directly to a C double bond O, which means that in the case of the alcohol, R does not have a C double bond O. If R does have a C double bond O directly attached to the OH, then we have to represent it separate from the alcohol. So again, alcohols and carboxylic acids are not the same. Another way of saying this, if you identify the characteristics of a carboxylic acid, the sets of atoms, carbon, double bonded to oxygen, single bonded to OH, the sets of atoms and their specific bonding patterns, we do not say that it is a carboxylic acid and an alcohol. That would be doubling up on what the OH is serving as. Does that make sense? Okay, a couple more. Amine is represented as RNH2, and I do want you guys to notice that there are a number of different ways that you can have amines. This specifically is a primary amine as opposed to a secondary and tertiary amine. Those terms are being used much like they were used to describe the carbons. Secondary amine has 2 carbon-nitrogen bonds. Tertiary amine, 3 carbon-nitrogen bonds. An amine is not the same and is not included in an amide. Those two have got to be the most challenging ones to keep straight because the difference in their name is 1 letter. And in a similar way, neither of these are related to the imine, in which you have this carbon-nitrogen double bond. Again, the nature of the atoms and the bonds that connect them distinguish these groups from each other. These all have very different groups, very different characteristic, very different reactivity. I think maybe there's one last one that I want you to know is not the same, and that is the ether, where oxygen is bonded to carbon on ether side. Did you catch that? Carbon on ether side is not the same as an ester, where the oxygen is bonded to carbon on either side, but one of those sides is the CO double bond. Esters do not contain ethers. Esters are not ethers because of the uniqueness of that CO double bond. Well, now that I've talked about that CO double bond so much, I want to give it a name. This in and of itself is not a functional group. The CO double bond is a bond type that we call the carbonyl. And so you'll notice that on your table, that whole left-hand bottom column is called carbonyl groups. They all contain carbonyls, but the carbonyl is not a functional group. The carbonyl is a part of many important functional groups. Does that make sense? All right. Here's the deal. I have an activity for us, but it requires that we get into new groups. So I'm going to have you, do you guys have questions on this before I have us move around? All right. I'm going to have you guys move around. You're going to make a line on the back wall from tallest on my left to shortest on my right. And while you get into that line, I'm going to put up instructions for you guys to do an activity. You will be sitting somewhere different, most likely, so it might be good just to bring just your work, but you probably don't need to bring all your stuff. No, Britain. Sorry, I think you're more this way. Sure. Okay. I've never actually heard a group like give numbers and say that we're 057s over here. Yeah, Hamza, I think, sure. Okay. A bit of an outlier. Okay, I'm going to assign you guys groups moving tallest and shortest together, and then coming in from the middle. We're going to have those groups as in the order that you're picked. Pick a functional group from this table, find a compound that has that functional group, try to make that compound relevant to your life, your field, whatever. Quick Google search, I promise you, you'll find a compound that's relevant somehow. And then I'll pause the recording. I'll have you guys come up and actually draw your compounds on the board so that you can highlight where that functional group is for the class. Do you have questions on this? So after I get you in a group, find a spot to sit so that you can work together and start thinking about what functional group you want. It's going to be first come, first serve. Okay? Selena and Ju. Lucky you guys actually do sit next to each other. Natalie and Britton. Perla and Calvin. Brenna and Kirsten. Carla and Layla. Hamza and Tanner. Wow. The friendship did make it through. Allie and Vivi.
Very easy.
Yep. Annie and Camilla. And then I'll have Jordan, Gabby, and Allie be a group of 3. Do you guys know what you want? Who did I have next? Britton and Natalie. Do you guys know what you want? Okay. Carboxylic acid is off the table. You want the amine. Good. Oh, man. You two next? The peroxide. Who was next? You two? It might have been.
Oh, I don't know. No, I just barely raised my hand for the first time, so if there was someone else.
I think it was you.
Okay. Esther?
Esther. And then I think it maybe was Layla and Carla. The nitrile. Yeah, I totally lost the order that I did it in. Were you guys next? Sure. Aldehyde. Hamza and Tanner? Alcohol. Who did I not do? Vivi and Allie? The sulfide. All right, Gabby, Allie, and Jordan. Nope, it's not up there yet. All right. All right, why don't I'm gonna pause the video now. Why don't you guys spend the next 7 minutes finding this and putting it up onto the board? All right? As soon as you're done, you can also take a break. Get up, move around, go to the bathroom if you need to. Okay, thank you everybody. And Let's give you guys a round of applause for that work. Ju and Selena, can I have you tell me what compound you picked with your carboxylic acid and why it was relevant?
We chose methacrylic acid because I'm studying material science. So basically any material in the dentistry. So basically that is a monomer that can be polymerized into polymethyl acrylate,
Nice.
which is used in like dentures or something. I don't know.
Very cool. So a polymer precursor, which we call a monomer. And you hear that term mer in there again, unit. Awesome, thank you guys. Britton and Natalie?
I kind of cheated. This is what I did for my organic compound. I don't know.
Yeah.
used propene, and it has an amine group, a secondary amine group.
Good, secondary amine.
Yeah.
You're welcome to call it amine. I don't know, that might be more of a biologist way to say it. I've heard that chemists and biologists pronounce a lot of things differently, but I'll refer to it as amine.
Okay.
Not trying to point that out, just good. Secondary amine as opposed to a primary or tertiary amine. And of course, by the time that nitrogen gets 4 bonds, it's no longer an amine, because a 4-bonded nitrogen has a positive charge. That's an ammonium. And the relevance you said was?
It strengthens collagen fibers.
Strengthens collagen fibers. Awesome. Calvin and Perla?
Benzoyl peroxide.
Benzoyl peroxide. What's it used for?
An
Acne
acne medication.
medication.
Acne.
Very cool. Peroxides, the OO single bond, are very reactive. Hydrogen peroxide, probably the most common peroxide there is. They will use them later in the semester to form radical species, and those radicals will go in and chain start reactions. Awesome. Very cool. Kirsten and Brenna, you had the ester?
I don't remember the name.
It is called linoleal acetate.
Linoleal acetate.
And it is responsible for some of the, it's an
Odorific. Love it.
that one smells like lavender or sage.
So this gives a sage lavender smell. Very cool. Thank you. Okay. Carla, yeah? And Layla. Thank you. The initials, they don't help me. What, you guys had nitrile, and you picked acrylonitrile, which is related to you.
Because it's in plastics and we decided we just love microplastics.
Love microplastics.
So they're everywhere. Like,
Good.
we're passionate about that.
This is likely another monomer to polymer starting material. Awesome. Gabby, Allie, and Jordan, you guys had ketone. How is this compound relevant to you?
That's Haldol,
Haldol.
yeah, which is an antipsychotic medication. I'm pre-med. Gabby is very
Pharmacy.
so we just did medication.
Nice. Antipsychotic medication. Very cool. Now your ketone has the carbonyl, CO double bond, and then a carbon on either side. That's the definition of a ketone. Specifically, yours can be described as an aryl ketone. The aromatic ring that is directly bonded to your ketone can be described as aryl. Of course, why would I just put it in air quotes when I can spell it for you? So we can describe it as not just a ketone, but an aryl ketone. Very good. Camilla and Annie, were you guys a group?
Yeah.
A lot of you sat next to the people you already sit next to. Great.
We did vanilla bean.
Vanilla bean. This compound is called vanillin, and it is responsible for that flavor in vanilla.
So a lot of things we eat.
Mm-hmm. Very cool. Thank you. How's Hamza and Tanner?
We have D-glucose.
Nice. Relevant to you because?
Your body uses it. We both took cell bio and learned how it works.
Okay, I don't know much about biology. I do know that there's a difference between D and L sugars. And I thought that D made you die and L made you live. Is that not true? L-glucose is not the one that is needed. It's D.
I think you use both, but D's the primary one.
Interesting. Okay. I must have misunderstood my biochem professor 10 years ago.
Maybe it's the opposite, where you'll die if you don't have it, and that's why.
Yeah, maybe.
And you assume that it was die if you get it, and live if you
You can live without it. The L you have to live without. I don't know.
Yeah.
Cool. And you pointed out that there are a lot of alcohols, but you actually have an arrow that goes to this O. Is this oxygen a part of an alcohol?
I don't know.
An alcohol is, at its basis, a carbon bonded to an oxygen bonded to a hydrogen. So we have to have a CO and an OH bond to have a carboxyl, to have an alcohol. There's no hydrogen connected to this oxygen, so we won't call it an alcohol. Instead, this oxygen has carbon on ether side. Ether. In fact, when you get into OChem 2, we'll describe this carbon with even more detail. The fact that this carbon has both an alcohol on one side and an ether on the other means that we can call it an acetal. Well, actually, this is a hemiacetal. It's halfway to an acetal functional group. So when common functional groups start to compound onto each other, they change the characteristics of that bonding pattern, creating new functional groups. I want to take this moment to actually point out, we said that the ether is ROR, but if those R groups are ever bonded to each other and you create a three-membered ring, it stops being an ether and it becomes an epoxide. And you might recognize epoxides from epoxy glues. They're very useful in holding things together, but this is technically not an ether because it has characteristic reactivity distinct from ethers. It's an epoxide despite sharing pretty much the same bonding pattern. The only difference is that R and R have to be connected to each other directly. Okay, our last one, Vivi and I imagine an alley. You guys had sulfide, so you picked?
Formaldehyde.
No, I don't think so.
Oh no, I'm so sorry because you wanted aldehyde and then it got taken.
I see.
Penicillin.
Penicillin.
Very, very good.
Yeah, I was like, actually formaldehyde is this compound, which is the smallest carbonyl compound that exists. And its name, formaldehyde, you can hear that it has aldehyde right in its name. But form actually also means aldehyde. So this name, formaldehyde, means aldehyde. As opposed to formic acid, which is an aldehyde carboxylic acid, because that carbonyl, that CO double bond, is both an acid, carboxylic acid, and an aldehyde at once. So aldehyde, acid, aldehyde. So fun. So you picked penicillin because? Good. Penicillin is a super funky little molecule. You see you've got this four-membered ring fused with this five-membered ring. There's a lot of what we call heteroatoms inside of those rings, and heterocyclic structures are super unique, challenging to synthesize, super important to life. Great job, guys. What questions came up while you were going through this activity? Anything? Britton.
So when you put R, it has to first connect to a carbon and then maybe the rest of
No.
Okay.
No, R does not need to be carbon. It's just often carbon. You guys will notice actually that I have the aromatic ring connected to R. And then in my example of an aromatic ring, I have nitrobenzene. And so I've created an R group where R is not a carbon. A lot of a lot of synthetic organic chemists will do different types of studies where they change both the position and the nature of a group relative to a group they're interested in. And then they will tell you down below when R equals H, when R equals methoxy, when R equals methyl. And they'll describe to you all of the different things that R can be. So it does mean rest of the molecule, and oftentimes it means carbon, but it doesn't need to. And that is confusing. The reason that I don't abbreviate alcohol as RCOH is because then it looks weird. What's going on with that C? It doesn't need to be a CH2. In fact, that language we were using earlier about degrees of substitution, methanol is a methyl alcohol. Ethanol is a primary alcohol. Isopropanol is a secondary alcohol. Butanol is a tertiary alcohol. We can start combining these different regiochemistry terms. Tertiary alcohol, primary alcohol. So I can't really abbreviate alcohol as specifically CH2 because that C doesn't need to have any hydrogens connected to it at all. So it's easier just to represent it as R and have you assume that R is carbon, but R doesn't have to be carbon. It's bad. I don't have a good answer for you. You'll have to squint your eyes sometimes and forget that it's there. Okay, anything else? Did you guys get the break you needed? You ready to move forward? Okay, I've got a new worksheet for you. We're going to continue on this train of regiochemistry, and we're going to talk about nomenclature. What do you guys know about nomenclature? Tanner, you want to share? You want to share? You were saying something about nomenclature.
Yeah, I said I never understood it, and I got every problem wrong. And I still have no clue.
Shoot. Well, I'm sorry to hear that. Let's see if we can change that then. Who can tell me what nomenclature means?
Isn't it naming molecules?
Naming molecules. Yeah, a system of naming. Have you used that word nomenclature anywhere outside of chemistry? Brenna, can you share? Where have you used it?
Everywhere. Anytime you have a system of naming anything, you can use it. Even in like music or math or like anywhere you look, you can find nomenclature of things.
Interesting. So I'm really just too isolated in chemistry to think that it's a chemistry word. I just don't understand where does that come from? Nomenclature? Is it Greek? Is it Latin? I don't see any roots in it to tear apart and tell you what it means.
It's just a fancy word for like.
Actually, I'm starting to think it's German. Is it German? Kind of sounds like say naming convention, but say it with a really thick German accent. Oh, okay. It's Latin.
Yeah, nomen is name.
I heard my dad say it all the time. Trying to be all smart. He's like, oh yeah, the nomenclature for this.
And nomenclature is notoriously challenging and unnecessarily tedious, and it will continue to be so.
It came from like the calling names referring to a steward or slave, and then it evolved to be the system of naming.
Okay, so literally name calling,
Yeah.
the names that you give people that you've enslaved. Holy crap. maybe we need to revisit this and decide what we are as a society. In organic nomenclature, we're going to break down a name into these 4/5-ish parts. Most names will have a prefix, and despite making up what looks like such a small part of this like generic name, the prefix will make up usually most of a name. A name will have a root. A name will sometimes have a locant, not always. And a name will have a suffix. Now, something that I like to add on to here, which is why I put it in parentheses for you, is that sometimes it will also have a suffix stopper. We can modify the suffix that we give it to give even more information about the compound. Let's start with the most pressing point, which is the root. The root is given for the parent chain, and we'll define the parent chain as the longest carbon chain containing the highest priority functional group and the most substituents. Oops. Substituents are a lot like constituents. Like in the American political system, we are all constituents of different representatives. We make up their representation. Substituents are groups that are on the molecule where hydrogens could have been. So a hydrogen has been substituted for this group. So substituents are the things that are put onto a carbon chain where a hydrogen could have been. There's a lot going on with that definition of a parent chain. Well, first of all, it implies that we have different priorities for different functional groups. Some functional groups will have a higher priority, meaning we want the longest carbon chain that has that group, not necessarily the longest carbon chain in general. And it means that if there is a carbon chain that is the same length in two different ways that you number it, you will go with whichever numbering has the longest length and the highest number of substituents. The roots that we give, this is what the first part of your worksheet will help us with. The first four feel a little uncommon and unfamiliar to most OChem students. If it's a one carbon chain, we give it the root meth. Okay, I know what you're all thinking. Methamphetamine has a one carbon chain on it, a carbon that's not bonded to any other carbons. Unfortunately, that's actually not the root. Amphetamine is the root of that compound, and really amphetamine is a common name. You can't really derive a lot of information out of it. One carbon chain meth, like methanol or methane. A two carbon chain, eth. Three carbon, prop. Four carbons, bute. By the way, I want you to notice that you've got a list of examples of what these carbon chains look like on your worksheet. These first four usually feel the least familiar in terms of nomenclature prefixes, but they feel the most familiar in terms of real life. Methane is in the news a lot. It's one of the most aggressive greenhouse gases after water. Ethanol is obviously the major component of liquor-based drinks. Propane, a very common fuel source when you're camping or cooking, as well as butane, common fuel source. So these 4 relate to real life, but they're usually nowhere else in chemistry. They're just in organic nomenclature. After this, things start to become more familiar. 5 carbons is pent, 6 carbons is hex, 7 carbons is hept. I really don't go this far very often, so I actually didn't give you anything longer than 6. 6 is the most common chain length that you'll have to get to, the highest, most common chain length you'll get to. But it does go on. Oct, 9, dec, undec, dodec, I think. I don't know. Because they're just not that common, we're not going to deal with them that often, okay? However, if your longest continuous carbon chain is cyclic, then the root is given a cyclo in front of it. Unfortunately, we can't have 2-membered rings. It's just not possible. But our smallest ring can be cycloprop, cyclobute, cyclopent, cyclohex. These are the most common ones that we'll deal with in organic chemistry. But they do go on. Cyclohept, cyclooct, cyclonon, cyclodec. As soon as you get familiar with these most common ones, the larger, less common ones are easy to understand and interpret. And you notice that the parent chain looks different if the root has cyclo or not. So I want to point out, cyclo is not a prefix to the root. It is now part of the root. If you have a 3-membered ring, you can't call it a propane structure. It's not propane prefixed by cyclo. It is cyclopropyl. So far on these structures, no functional group other than the carbon-carbon single bond, which is what functional group? Carbon-carbon single bonds? Alkane. In fact, a lot of people will say alkane is not a functional group because it is the bare minimum for being an organic molecule. It's so common, it's so prevalent, it's so unreactive that a lot of people don't call alkane a functional group, but in general, I do. All right. You have this string of molecules along the bottom. I want you to decide what root should be given for the longest continuous parent chain, for the parent chain, the longest continuous carbon chain. Go through them, talk with your neighbors, decide what root should be given in each case. Which one is longer? Go with the longest.
Well, technically, all the carbons is actually in the ring.
They don't have to.
Yeah, that's why the root can be cyclic.
So you count 1 to 4 extras. You know what I'm saying?
I do know what you're saying. No, because that's no longer continuous.
But are they all connected?
There is no beginning or end within the ring. So it can either be cyclic in the ring or it can be linear outside of the ring, but it can't be both. It is a good question. That's why I have them on there.
Because there's 5 in there. 1, 2, 3, 4. So
Good. Not 4. 3.
oh, because it can't, if that carbon is in the ring and it's not.
Good.
Will this also be 6?
Okay, here's a very common question that comes up. Can I count every carbon, both inside a ring and outside of it, as a continuous carbon chain? And the answer is no. You can either count carbons within a ring, or you can count carbons in a linear chain, but you cannot count a continuous carbon chain with carbons both inside and outside of a ring. So a tip for identifying this: find the carbon in the ring that bonds to the carbon outside of the ring. Mark this line. The carbon to the left of that line is included in the ring. The carbon to the right of that line is excluded from the ring. So here I have 5 carbons inside of the ring and 3 carbons outside of it. What root should I give my longest parent chain? My parent chain. Sorry? Yes. Which one? What root should I give? Cyclopent. Not just 5, not pent, right? The root for this compound is cyclopent. What about my first compound? What is the root given? Bute. So I want you to notice that there is a way to count a 3-carbon chain in that compound, but that's not the longest possible carbon chain. There are 2 different ways that you could number and get a 4-carbon chain. So our root here is bute. Our root here is cyclopent. We'll have to describe these carbons as a substituent to the root. They come off of the root. What about my next structure? What is the root that I give? Hex. I'll look at this line again. The bond between the ring and outside of the ring. Now I've got 5 and 6. So now my ring is not the longest carbon chain, and I have hex as my root. And the last one, cyclohex. Once again, I have 2 different groups. I can't count all of those carbons as one continuous chain. So I have one group with 6, one group with 3. Questions on that? Great. Easy enough to cut a ring from the groups that it's connected to and count one or the other? Kirsten?
So for the butte, I noticed that you put the 1 at the top and then counted down from that. Could you put the 4 on the other side?
Yep.
Or is it specifically to that?
So first of all, I could have counted from the bottom. I could have counted up. I could have counted from the left. I could have counted down to the left. I'm just identifying the longest carbon chain.
Okay. I was looking in the book.
We are going to assign locants using those numbers, but that's a different process. We're not on the locants yet.
Maybe that's what I was confused by, because I was like, it was saying one thing and then it was showing another one and it was like, this is not right.
Yeah.
Of this. And I'm like, but it could work.
Here, maybe it would have been better at this point to be a little bit more symbolic. No numbers, because we are going to use numbers at another point, and just say 4 carbons is greater than 3. You're onto something, but we're not there yet.
That's totally fine. I just knew that that was a question that I wanted to ask.
Good.
but I figured I'd ask.
The next component that I want to consider with you guys is the suffix and the suffix stopper. The suffix is given by a hydrocarbon functional group. What are the hydrocarbon functional groups? Britton's got it. Good. All of those hydrocarbon groups are put together as a family on your table of functional groups. Alkane, alkene, alkyne, and the aromatic ring, the arenes, the aryl groups. If the highest priority if the only functional group is alkane, then we give it the suffix ane. That's how our name will end. We take the root and we add ane to the end. Methane, propane, butane. Alkene gives it the suffix -ene. Alkyne gives it the suffix -ine. Remember how some people don't believe that alkane is a functional group? So if there is any other hydrocarbon besides alkane, they just drop alkane and they focus on the hydrocarbon present, alkene or alkyne. But if both an alkene and an alkyne are present, then you have another combination, which is the -ine suffix. It has both -ene in the suffix and -ine in the suffix. And you'll notice I'm using these hyphens to separate those two components because there are locants that actually go in there to describe where along the carbon chain does that hydrocarbon group show up. I've got this many carbons. Where along that carbon chain does this group appear? Those are our suffixes. Our suffix stoppers come from higher priority functional groups. Alcohols, carboxylic acids, ketones and aldehydes, amines. And they don't have their own suffix. Instead, they modify the suffix of the hydrocarbon. So suffix stoppers for our class, the only other suffix stopper that we're going to work with is the alcohol. And it gives the stopper OL. What that means is that you have to have a suffix from a hydrocarbon. And then you can drop the E at the end of that suffix and stopper the suffix with OL. For instance, if you have CH3OH, that's an alcohol functional group, 1 carbon, methanol. It's not methyl. It's not that OL is the entire suffix. Instead, it's methanol. So we get combinations like anol for an alkane that has an alcohol functional group. We have enol, which you guys will actually notice on your functional group table is a functional group in and of itself. An alcohol bonded to an alkene is referred to as an enol, and that's how the compound is named. You can have an inol. Notice how the last E in all of these cases, it's just being dropped. So what if your compound has an alkene functional group, an alkyne functional group, and an alcohol functional group? Then you have all. Old MacDonald had a farm. Enine, You get all these combinations. These are all possible ways to end the name of your of your compound. And they describe the hydrocarbons present and the alcohol group present, if possible. Deal? In OChem 2, we'll dive more into the nomenclature of other groups, and we'll dive more into the nomenclature of aromatic rings. That's what I'm doing with OChem 2 tomorrow. We're doing aromatic rings, not because it's necessarily harder, it's just not relevant until then. All right, so here's what I want you guys to do. I want you to find the longest, oh, sorry, I want to talk about priority. Our highest priority functional group in this set, not out of all functional groups total, but in this set, our highest priority is alcohol, then alkene and alkyne tied, then alkyl groups and halogen groups. Alkyl here is a word that just means R groups. Kind of like in the way that halo means halogen groups. And actually, the name alkyl is a very interesting nomenclature excursion on its own. Did you notice how all of our hydrocarbons, except for the aromatic ring, all of our hydrocarbons start with this ALK component? ALK there represents carbon bonding, carbon groups. I don't know where it comes from or what it means really, but every time you see ALK, it's referring to carbon groups. This suffix YL is a very common suffix to describe being a substituent. Not the parent chain, not a part of the root, not included in the suffix, but a substituent to the molecule, a group coming off of the parent chain. So this is a carbon substituent. This is what alkyl means. And we'll have very common substituents like methyl, ethyl, propyl to indicate what carbon length is acting as a substituent. So here's what I want you guys to do. On the bottom here, I want you to find the longest continuous carbon chain that contains the highest priority functional group. And then give both the root and the suffix. And the suffix stopper if necessary.
Then we don't have to do that. Okay. Is this an alcohol? The weight?
The parent.
So that's 6, right?
The parent is not the longest carbon chain. It's the longest carbon chain with the highest priority functional group.
So it's 2?
That's actually not continuous.
Okay, so it would just be this. Okay, so it is this.
No, because that doesn't include the highest priority group. It doesn't include the alkene. And the alkene, since there's no alcohol, the alkene takes priority. So my recommendation would be start where the alkene starts and find the longest group that contains it. Are you seeing why I picked the examples I did? It's to highlight that when there is a higher priority functional group, you don't always go with the longest carbon chain. For instance, you can find 6 carbons across on the compound with this alkene, but then you don't actually include the alkene. You've got 1 carbon of an alkene, but an alkene is defined as a carbon-carbon double bond. If you've got 1 of the 2 carbons, you don't have the alkene. So instead, we find the parent chain, the longest carbon chain, including the alkene. Let's start where the alkene starts, and then go in the direction that finds the longest carbon chain. This is our parent. It's not the longest continuous chain. It's the longest continuous chain with the highest priority functional group. This 2 carbon segment over here, This will now be considered an alkyl substituent to the parent. Pentene.
Because of the double bond.
Yep, so pent is the root, ene is the suffix because of the alkene. Pentene.
Is a dead parent.
No, it's not. In the alcohol, what is the longest carbon chain? 2 carbons, so that gets the root, eth, the suffix ane for alkane, and then stoppered by all, so we get ethanol. And now we will describe cyclohexyl as the substituent. We'll get more into that when we come back on Wednesday. Cyclohexyl. That YL, again, tells you that it's just a substituent. It's not the parent, so it doesn't get the suffix. It gets YL. What is my longest, what's the root for my longest carbon chain here? Prop. And the suffix? Propyne. And this one will actually have a dicyclopentyl substituent. It has 2 groups that are identical, and they're both 5-membered rings. So we'll come back and talk about how to add substituents into the prefix on Wednesday. Taking up a minute of your night. Get out of here. Have a good night. Start on your homework. See you Wednesday.